So as you know, my name is Gottshe. I will teach the course in algebra. So maybe first some general remarks. So this is a rather elementary course. So first course in algebra, which covers groups, rings, fields, and Galois theory. So many of you might know it, or at least part of it. And so it's quite basic. So still, I want you to pay attention and take it seriously. Maybe there are some things you don't know, and otherwise, maybe nice to repeat it. And it's always important to understand the basic things before one can move to the more advanced ones. So, so understanding means that you really know what the definitions and theorems mean, how you can use them to prove theorems yourself, and how you can build on it. And also, you have to be able to solve exercises. So you will get exercises maybe more or less every week, and I would like you to really solve them. I don't believe very much in hard exercises. My exercises are supposed to be easy. But that means also that you should be able to solve them. If you can't solve them, then there's something wrong, and one has to, you have to ask me or the tutor, only blessing, how to do, and you have to maybe work more. But normally, these exercises should be quite easy. So it's just a way that you can test whether you have understood the theorems and the definitions and can apply them in a basic way, and maybe have some simple thoughts about them. Okay. So now let me start. So I said we talk about groups, rings, and fields. So let's start with groups. So you will have to get used to my handwriting, but it's I think people usually have some problem the first lecture, but afterwards they find it very easy to read. So the concept of group is a very basic concept, a fundamental concept of algebra and of mathematics. So it just is a set whose elements we can multiply, and there are also multiplicative inverses, and some of the usual rules you are used to from arithmetic apply, so the most basic ones. So let me write the definition. So a non-empty set B with a binary operation which I write times from G times G to G. So I send a pair of elements AB to something which I denote A times B, or also just AB. Which this one calls the product, is called a group if the following axioms hold. Well, the basic things. So we need the associative law. So that says A times B times C. If I do the product like this, first I multiply these two, and then I multiply this from this side, it's the same as if I do it the other way around. And and this is supposed to be true for all elements in G. And then we can also write this just, if we want, as ABC. Because the brackets don't play a role, we can also leave them out. Then the second is we have a neutral element. So there's one element which doesn't do anything. So there exists an element E in G such that E times A is equal to A times E is equal to A for all A in G. And then you have an inverse. How do I want to divide this? Well, okay. And then finally, we have an inverse for every element. So for all elements A in G, there exists an element A to the minus 1 in G, such that A times A to the minus 1 is equal to A to the minus 1 times A is equal to E. This element E, we also usually write 1. No, like we do for integers. So this is just this definition, very simple. I make some trivial remarks, which you most likely also already know, namely some basic things that one immediately can prove from the axioms. And if you don't see it immediately, you can do it yourself. So first, the neutral element is unique. So if we have two neutral elements, they have to be equal. The inverse is unique. And furthermore, it has to be an inverse only on one side to be the inverse. So, and if EA is equal to E, then it follows that B is equal to A to the minus 1, and obviously the same on the other side. And, well, whatever, some other trivial things. If you take the inverse of the inverse, this is the original element. And if we take the inverse of the product of two elements, this is the product of the inverses the other way around. And so these are all obvious. That means you just apply the definition, you do the obvious thing, and it follows. And so I will not, so this is an easy exercise. Okay. There's one simple property which is about as easy, which I still note because it's somewhat useful, cancellation property. So this just says that if you have an equation of elements in G, we can cancel the same factor in the equation. So G is a group, so let mark let A, B, C be some elements in the group. So if AC is equal to BC, well, okay, why not BC? Then it follows that A is equal to B, and if CA is equal to CB, then it follows also that A is equal to B. And this is again obvious. You just multiply by C to the minus 1. So some groups have nicer properties than just being a group. So many groups you're familiar with, like the integers, have the property that they are commutative, so that the order of the elements doesn't play a role. So I just write it down, definition. A group G is called the Abelian. It's actually written large because the name Abelian or commutative. If whatever, the product, the order in the product doesn't matter. So AB is equal to BA for all AB in G. Okay. And then, as usual in mathematics, most of the time when one has an Abelian group, one writes, instead of the product, one writes it additively. So usually you write Abelian groups. additively, namely, well, I don't know, additively. So that means we write a plus b instead of ab minus a for a to the minus 1, and say a minus b for a b to the minus 1. Okay? So like one writes things in the integers. Okay. So now let's look at some examples of groups. I mean, you're familiar with many examples, but I can write some more. Or maybe just repeat the examples, just to have it written once. So for instance, the integers with addition. So integers with addition are an Abelian group. Obviously, the neutral element is 0, and the inverse of A is minus A. Of n is minus 1. So we can look at another example you're also familiar with, computing modulo some number. So we take k, some positive integer. And we look at the set, say, which I call here zk, which is just the integers from 0 to k minus 1. So we want to make this into a commutative group. So, and we do this by somehow using the addition in Z. So for integer n in Z, we let R of n be the rest that we get if we divide n by k. That means we can write n equal to d times k plus r of n, where d is an integer, and r of n lies between 0 and is smaller than k. So, and then we do the obvious thing. We define the addition on this zk by saying by setting the sum of n plus m in zk, by defining it to be, we first take the sum of n plus m in Z, and then we take the rest. So this is in ZK, and this here is in Z. And then it's easy to check. So it's an easy exercise. Check that this makes ZK into an Abelian group. And obviously the neutral element is 1, is 0. And the inverse of n, so inverse of an element n, which lies between 1 and k minus 1, is k minus n. Okay, that's from the basic properties of arithmetic, what it means to divide by a number. That is what follows. So another maybe more interesting group is permutation groups. So let M be a set, maybe a non-empty set. So the group of permutations of M. So I denote it SM, which is just the set of all bijections from M to itself. So bijective map from M to itself. And this is a group with a composition of maps as multiplication. So F times G I define to be F composed with G. Okay, so obviously the neutral element is identity. And the inverse element of F is the inverse map of F. Because after all, multiplication is composition. And so that this is a group basically is the statement that composition of maps is associative. Okay, so a special case of this is maybe more familiar, namely if we just look at all the permutations of the numbers from 1 to n. So this will be is called the group of permutations in n letters. So, or the symmetric group in n letters. Yeah, I wanted actually to call it differently. Well, anyway. Or symmetric group. On M. So the symmetric group on n letters is just the symmetric group. So I write it Sn. This is the set of permutations of the set 1 to n. So all the bijections from the set from 1 to n to itself. So all the possible reorderings of one of the set of numbers from 1 to n. So this is now a special case of number 3. And so we can write an element F in Sn in the simplest way as by just making some kind of list. The number 1 goes to f of 1, 2 goes to f of 2, n goes to f of n. This is some way how one could write this. And obviously the neutral element E is just one which sends every element to itself. Okay, and you can check. It's expect you know it, but it's easy to check that, for instance, S2 is abelian, and Sn is not abelian for n bigger than 2. You could just write down some elements which do not compute. Another example, or just a way of constructing more groups from others, is the product of groups. So I tell you these elementary things also to introduce all the notations that I can use freely afterwards. No? So the product of groups so just the direct product of groups. So if G and H are groups, we define the product group is just the set theoretic product, G times H, so which is the set of all GH H and H, and with component-wise multiplication. So with with component-wise multiplication. So that means if I take GH times G prime H prime, this will be just G prime H prime. And this is obviously a group where the neutral element, so it's a group, well, I said it's a group, the neutral element is just if, say, E is the neutral element of G and E prime is the neutral element of H, this will just be the pair E prime, and the inverse is just a part of the inverses. So inverse of GH to the minus 1, H to the minus 1. All of these are quite obvious, or maybe even a bit too obvious. Okay, so these were these examples. So maybe I wanted to think one more example, just one which you're also very familiar with, which is matrix groups. So maybe this is number 7. So if so I write that L N R can't at least be the group of n times n matrices with entries in R in the real numbers. And this is, as you know, a group under matrix multiplication. What? Ah, yeah, I forgot to say that, yes. Yes, so I was a bit too fast. So I call them G, A with set of A different from 0. So with non-zero determinant. Okay, thank you. I mean, obviously. So this is a group matrix multiplication. And obviously, the neutral element is the identity matrix. There's 1 on the diagonal and 0 everywhere else. Okay, so if one thinks, I mean, for the moment, it's always good to have some examples in mind when one studies some results. So for the moment, maybe as example of a commutative group, you might want to look at, you might keep the integers in mind, which is the simplest example that one can think of, more or less. And then for non-commutative groups, one could think of the symmetric group and this group of matrices. Later we will, yeah, anyway, no, maybe we will not go into this now. So, what else do we have? Ah, yeah, I maybe should have mentioned this as I already used it. So obviously, this GLNR is non-abelian for n bigger or equal to 2, as you are very well aware. And when n is equal to 1, it's just the real numbers with multiplication, the non-zero real numbers with multiplication. Okay. So one more. So we have some groups here which are finite, some groups which are infinite. So I just introduce a word for the number of elements group, which is called the order, and introduce some notation. And at some point we can actually start. So, definition: the order of a group G noted just like G in absolute value is the number of elements of G. And this could include, I write infinite if the number is, if the group is not finite. And I call the group finite, obviously, if the number of elements is finite. And so, for instance, you can check from the definition that the order of the symmetric group in n letters is n factorial. So that follows from the definition with, if you think what you can do. I also want to introduce the basic power notation, although I expect if I would use it without introducing it, you would also not mind. So G is a group. A is an element in G. Then we can write, so if n is bigger than 0, just write a to the n for a times a, n times, as you are used to it. A to the minus n is same with a to the minus 1. So or you could also say it's a to the minus 1 to the n. And obviously a to the 0 is our neutral element. Okay, this is this notation. And if we can also write, if the group is written additively, we instead write multiple. So if G is written additively, you write NA for a to the n, for n in Z, for a to the n. And you can check by some easy induction that if I take a to the n times a to the m, for n and m integers, is equal to a to the n plus m, and a to the n to the m is equal to a to the n times m. Okay? Like you're used to from school. Okay, so that was basically the definition of a group. Now we come to subgroups. So we want to say when is, what's the subobject of a group? So when is a subset? So a subgroup of a group should be a subset of the group, such that if we restrict the multiplication of the group to the subset, you get a group. And so I first say it, so subgroups. So definition, let G be a group. H in G, subset, non-empty subset. So for the moment, I just say H is a subgroup of G. And this is sometimes denoted, but I don't think I use this very much, H smaller than G. If, well, I just say it, it's not the most practical definition, but this is what it is. So if for all A, B in H, we have A times B is in H, and with the restriction of the multiplication from B times G to H times H, H is a group. I mean, that's in some sense clear that this is what it means that the subgroup is, but there's some easy criterion to check this, which is also often taken as the definition, namely, it's the following remark. So a non-empty, so if H in G is a non-empty subset, then this is a subgroup if and only if well, so for all A and B in H, we have A times B is in H, and we also have, and for all A in H, we have A to the minus 1 is in H. Or equivalently to these, one can also put it together in one criterion, in one condition, although that is usually not easier to apply than doing these two. So equivalently, for all A, B, and H, we have that A times B to the minus 1 is in H. Okay, so it's easy to see that this condition will imply this, and then, and so this is quite straightforward. I also leave it as an exercise. So you want to show that under this condition, H with the multiplication, the restriction of the multiplication from G is a group, and that follows quite immediately. So the neutral element of H will be obviously the same as the neutral element of G. Okay, so this was this definition. So now we want to, I give again some examples of subgroups, because it's always good to have some examples. So for instance, in Z with the addition, we can just take Kz, which is the set of all K n with n in Z, where K is an integer. is a subgroup. Okay. Now, obviously, if you add kn, kn1 plus kn2 is equal to k1 n1, k times n1 plus n2, so that's kind of obvious. So then one nice, so if an intersection of two subgroups is a subgroup. So if H1, H2 are subgroups of G, then H1 intersected H2 is a subgroup of G. This follows immediately, for instance, from this criterion. So for any element H, any two element in H1, if you have an element which lies in H1 and in H2, then by this A, b to the minus 1 also lies both in H1 and H2, and therefore in the intersection. Okay, so one can, in fact, one can also do the same for intersections of infinitely many subsets. So if Hi, I in I, so some possibly infinitely many subgroups are subgroups of G, then their intersection is intersection over all I in I, Hi is a subgroup of G. I mean, just to be on the safe side, it's clear that if you take the union of subgroups, there's no good reason why that should be a subgroup. And it usually won't be. But one can do something else, namely one can take the subgroup generated by something. So let G be group, and S is subset. Then we can look at the smallest subgroup of G, which contains S. So the subgroup of G. Can you see it when I write here? Generated by S is, well, I can use this previous example. It's just the intersection over all. Maybe I don't have enough room here. Yeah, so is the intersection over all H subgroups of G such that S is contained in H. So this, and I denote this S. Subgroup generated by this. So this is, from this definition, we see that this is clearly is the smallest subgroup of S containing of G containing S. And now, from the definitions, you can check. This is an exercise which is maybe, well, I think it's still quite simple. Basically, the definition, we can describe S as follows. I mean, more explicitly, it contains the following elements. It's given, its elements are products, G1 times Gn, where n is some non-negative integer, so there can be an arbitrary long product of elements. And for all I, from 1 to n, we have that either GI is in S, or GI to the minus 1 is in S. Okay, then the bracket closes. So that means the subgroup generated by S can be written as the set of all, if you want, words. So where the letters are elements of the group, and each of the letters is either an element of S or in the inverse of an element of S. You can easily check that such a thing will be a subgroup, because if you use this criterion, it will be a subgroup, and clearly it contains S. So therefore, and any subgroup which contains S must contain all these products. And so therefore, it follows that this is, so I solved the exercise for you, except for writing it down. So a special case of this is, for the moment, more important for us, a much simpler case, namely the subgroup generated by one element. Somehow the simplest kind of group is done like this. So J is a group. A is an element in G. So the cyclic subgroup of G generated by A, so I denoted A. And if I look at this definition, it's just the set of all powers A to the n, where n is in Z. And this is obviously a special case of the previous one, where obviously the multiplication of these is by adding the powers. This is clearly a subgroup. Okay, and so we call a group G is called cyclic. They're somehow the nicest groups. If we can write G equal to the group generated by A for some element. So if it's generated by one element of G. Now, here that cyclic groups are abelian. No. A to the n times A to the m is A to the n plus m. Okay. Maybe there's more. Okay. So for instance, as an example, that is cyclic, is generated, for instance, by element 1, and also Zk is cyclic, also generated by the element 1. So cyclic groups can be both infinite and finite, because obviously any element of Z is obtained by as n times 1. So now we want to see that if we have a subgroup in a group, it gives us a decomposition of the group into equivalence classes, which will be called the cosets. And we will then also see that all these cosets have the same number of elements, namely as many elements as the subgroup. And from this, we get our first little theorem, which says that the number of elements of a subgroup of a finite group must divide the number of elements of the group. So let's do this. So first, I want to briefly review equivalence relations. I expect you're aware of it, so I will maybe do it without proofs. So first, I mean, just to keep be on the same footing with the notations. So if A is a set, so a relation on A is just a subset of the product of A with itself. Okay, you say we write A is related to B if the pair A comma B is an element in R. This is just a relation. This is so general that it's almost completely useless, but a special case of a relation is an equivalence relation. So R, a relation R, is called an equivalence relation if it fulfills three properties. If, say, for all A, B, C in A, we have the following properties. First, we have the reflexivity. So A is always equivalent to A. We have the symmetry. A is equivalent to B, then it follows that B is equivalent to A. And third is the transitivity. So if A is equivalent to B and B is equivalent to C, then it follows that A is equivalent to C. So these are, I think you have certainly seen this. These are the simple properties. Usually in real life, most of the time, the first two will be obvious, and the second one might require a little bit of work, but it's not always the same. And you can think of an equivalence relation somehow that you have two things are equivalent if they have a certain property in common. No? So obviously, everything has this property in common with itself because it has this property. If A has a property in common with B, then it's also the other way around. And if A and B have this property in common and the same property B and C have in common, then also A and C have this property in common. So that's somehow, in some sense, the notion of equivalence relation encodes this idea of having some property in common. And now, if we have an equivalence relation, we have a decomposition of A into equivalence classes. So definition. Let A be a set. And this an equivalence relation on A. So the equivalence class of an element A in A is denoted by A. And this is just a set of all elements which are equivalent to A. Okay. That's the equivalence class. And we can maybe rewrite A divided by equivalence for the set of equivalence classes. some sense, the idea is here that we, in some sense, identify as one thing all the things which are equivalent to A. But we do this by just viewing all the things equivalent to A as one object, one set. And then looking at the set of these sets. Anyway, so now the easy fact is that these equivalence classes are always either equal or disjoint, and their union is the whole of A. And so we have a decomposition into equivalence classes. I think I will also not, so this should be an equivalence relation on A. So the distinct, first say it in words, equivalence classes give a decomposition of A into disjoint sets. So what I'm saying here is two things. First, the union over all the equivalence classes is the whole of A. And the second statement is that two equivalence classes are either equal or disjoint. So if the class of A is different from the class of B, then A intersected B is the empty set. Okay, so I mean, I will maybe not really prove it. It's also obvious. So here it's clear. We know that A is in the equivalence class of A. So it's therefore clear that all elements in A lie in the union of all the equivalence classes, because each element is contained in its own equivalence class. And here one makes a slightly indirect argument. We assume that A intersected B is not the empty set. So we take an element in A intersected B, and then we can easily use this element to show, I mean, maybe we can just say, as I sketched it, that X be an element in A intersected B. Then it follows that, so as X is in A, we have that X is equivalent to A, and also X is equivalent to B. So thus, say A, if I use a symmetry here, A is equivalent to X, and X is equivalent to B. So thus it follows by transitivity that A is equivalent to B. And from this, we easily see that A is equal to B. Okay. Yeah. And now we want to do this look at this for subgroups. Now we assume we have a subgroup in a group, and then we want to see that this defines an equivalence class whose equivalence relation whose equivalence classes will be the cosets. So let me introduce this cosets. So as I said, a subgroup H in G determines equivalence relation on G, whose equivalence classes are the cosets. Anyway, so let's define this property. We take a subgroup. For an element A in G, we call AH the set of all AH with H and H. The left coset of H in G. So it's left because A is on the left. You can also talk about right cosets, but that really doesn't make any difference, and so I just stick to the left ones. So clearly, by definition, one of these cosets is H. If I take one H, so one, the neutral element of G, this is equal to H. So H itself is one of these cosets. We can also define an equivalence relation. An equivalence relation say tilde on G depending on H. Namely, we say that what is it? We say that A is equivalent to B, A and B are elements in G, if and only if there exists an element H in H such that A is equal to B times H. So it's easy to check. This is an equivalent relation. Relation. No, it's obviously symmetric and reflexive, and yeah, I mean, anyway, it's easy to see. And the cosets are the equivalence classes. That means the class of A is equal to AH. No, I mean, you can, that's basically the definition. So therefore, by this previous statement, we have a decomposition of G into disjoint cosets. Of G into disjoint cosets AH. So now I want to come to this result that the number of a subgroup, the number of elements in the subgroup has to divide the number of elements in G. So we want, therefore, to see that all the cosets have the same number of elements, and in fact, the same number of elements as H. So mark. So we take an element A in G. Then the map from H to AH, which sends an element H to A times H, is a bijection. So in particular, if H is finite, it has the same number of elements, but otherwise, they are H and AH are bijective to each other. And this is clear because we can immediately write down the inverse map. We just multiply by a to the minus 1. Map from AH to H, which sends an element G to a to the minus 1 G. These maps are obviously inverse to each other. Okay, so that means if H is finite, every coset has the same number of elements of H. Also want to introduce how many cosets, a name for how many cosets there are, because we will need this in the future. So again, let H be, so this is the definition. So let H be a subgroup of G. So the quotient set G mod H is just a set of left cosets. Okay, AH, and the index of H in G is the number of left cosets, so is G H, like this, G divided by H in brackets, which is defined to be the number of elements in G mod H, where, again, this could possibly be infinite. If there are infinitely many cosets. So this is the index. And then with this definition, we have our first theorem, which is incredibly simple, but very useful. Namely, this is the theorem of Lagrange. So let G be a finite group. H a subgroup. So then the order of H divides the order of G. More precisely, we have that the order of G is equal to the index of H in G times the order of H. Okay. So this is a theorem because it is very useful, but it is also kind of trivial because there's nothing really to prove. We have already proven it. So we know G is the disjoint union of index of G and H cosets, each of which has the same number of elements, namely has H elements. So at least once one has this whole setup, we have it immediately. Now we want to spend a little bit of time by giving a few consequences, elementary consequences of this theorem. So first make one more definition. I have defined what the order of a group is. One can also define what the order of an element is. The order of an element is the smallest power of the element, which gives you 1, the neutral element. So definition. So let A be an element in G, where G is a group. The order odd A of A is the smallest positive integer with A to the n is equal to the neutral element 1, if such an n exists. Otherwise, I say the order of A is infinite. So, for instance, in Z, with the addition, we have that the order of 1 is infinite and the order of 0 is 1. So in this case, obviously, the neutral element, so in this case, it's not 1, it is always the neutral element. So here the neutral element is 0. So here it would be n times A is equal to 0. Okay. So the first corollary is that the order of any element has to divide the order of the group. Let G be a finite group. Then order of A divides. Okay. And A an element in G. And the order of A divides the order of G. So let's prove it. So we look at the cyclic subgroup generated by A. Okay. So we wanted to use Lagrange's theorem, Lagrange's theorem. So we have to find a subgroup. The subgroup we take is this one. The claim is that the number of elements in the subgroup is equal to the order of A. So claim that the order of A of the subgroup generated by A is equal to the order of A. And this claim proves the corollary. Okay, so more precisely, we claim that this cyclic subgroup, we can precisely say what its elements are. They are 1, A, and so on, until A to the order of A minus 1. And all these elements are distinct. So therefore, manifestly, it has order of A elements. Okay, so let's see. That's quite simple. So by definition, we have that A is just the set of all A to the n with n in Z. So let's take, so if we take an element, it will be written as A to the n. So let A to the n be an element A. We have to show it can be written like this. So we make division with rest in Z. We can write n equal to order of A times d plus rest r, where d is some integer, and r is between 0 and the order of A minus 1. Then if we take A to the n, this is A to the order of A times d plus r. This is A to the order of A, which is 1 to the power d times A to the r, which is equal to A to the r. So we have seen that we can write every element of A as one such power between 1A until A to the order of A minus 1. So that's 1/2 of it. And the other one, we have to show that these are all different. So assume that we have 0 is smaller or equal to R2, smaller than R1, is smaller than the order of A. And with A to the R2 is equal to A to the R1. Well, then we can divide by A to the R2, and so we get A to the R1 minus R2 is equal to 1. And obviously, we have that 0 is smaller than R1 minus R2 is smaller than the order of A, which contradicts our definition, is against our definition. So therefore, we have indeed this corollary. So this cyclic subgroup has precisely these elements, and therefore it has precisely order of A elements, and therefore the order of any element has to divide the order of the group. How much more time? Oh, quarter of an hour. Okay. A simple consequence of this is also so if G is a finite group, I can ask myself, again, we take an element, then I can ask myself, what happens if I take A to the number of elements in the group, and this will be equal to the neutral element. And this is easy consequence of what we just did. Namely, we know that odd of A divides the order of the group. And so we can write, so I can write G equal to the order of the element A times some integer D, positive integer D. And so A to the G is equal to A to the order of A times D, which by the same argument as before is 1 to the D, is equal to 1. And the final corollary is that if a group has as number of elements a prime number, then we can understand it completely because it will be a cyclic group. So corollary let G be a finite group of order P equal to P, prime number, then G is cyclic. Okay, now that should be also quite clear. One just takes any non-zero, any element which is not the neutral element, you take the subgroup generated by it, and it has to be the whole of G because there's not room for any other subgroup. So proof. So P as 1 and P as only non-negative divisors. So it must therefore be that the number of elements of a subgroup is either 1, in which case the only possibility is that it's a group consisting of 1. So thus, if H subset G is a subgroup, then H is equal to 1, or H is equal to the whole of G. Now it has either P elements, and it must be the whole group, or it has one element, and it must be just 1. So now let A be an element of G, which is different. So let A be an element of G, which is different from the neutral element. As the number of elements is a prime number, if the number of elements is not 1. And so then A is a subgroup, has more than one element, so is different from 1. So the subgroup represented by A is equal to G. And so the group is cyclic. Okay. That, I think, was more or less where I had. So now this is as much as I wanted to say for the moment about subgroups. Now we want, maybe mostly the next time, but I can already start, talk about normal subgroups, which are particularly nice subgroups. So normal subgroups. So for me, the motivation comes from a natural question you could ask yourself. Namely, if H in G is a subgroup, we can form the set of cosets. So, and we can ask ourselves, is that in a natural way a group? Is B modulo H, so the set of all AH with A in G, in a natural way a group? What do I mean by in a natural way? Well, the obvious thing that one would want to do should give us a group. The obvious thing is that we say AH times BH should be A times B times H. With the product AH times BH is equal to ABH. Now, it seems an extremely natural definition. One could think that this will always work. We have written it down, but you have to ask yourself whether it makes sense. Now, because we have said the product of AH and BH in terms of A and B. So if we take other elements in AH and BH, one says other representatives, will the result be the same or not? No? Let's say, so will this product be well defined? So we need the product to be well defined. That means this definition to make any sense. So that means we need that if AH is equal to A prime H and BH is equal to B prime H, we need that ABH is equal to ABH is equal to B A prime B prime H. Let's just check this for one example. So let's just look at a special case. So we put, for instance, we can take A to be just a neutral element, A prime, H, in H a general element of H. And I can even take B equal to B prime in G, a general element. Then we just write down what this condition says. Then we want that A times B, so this is that BH is equal to HBH. Or differently, that I can write, okay, so we can multiply by b to the minus 1 on the other side. So this is equivalent to saying that b to the minus 1, HB, is in H. And if we want this to be true for any element in H, so and for any element in G, we get the condition, so which is necessary for this to be well defined. We need that this is true for all B in G and all H in H. So we have found here a condition which is necessary for this definition of the product in the quotient to make sense. Okay, and this is the definition of a normal subgroup. In a moment we'll see that there are many subgroups which are not normal. Definition: a subgroup H contained in G is called a normal subgroup If G, H, G to the minus 1, so here I replaced, so G is our B to the minus 1, is an element in H for all H in H and all G in G. So this is the definition of a normal subgroup. So we can give just a couple of examples of subgroups which are normal or not normal. So examples. The first, if G is abelian, then every subgroup is a normal subgroup. Okay, that's obvious because we want GH, G to the minus 1 in H for every H in H. So we just bring G to the other side. So GH, G to the minus 1 is just H. And so that's certainly true. So let's look at an example of a subgroup. So yeah, maybe one other trivial example. So 1 and G are normal subgroups. G. And let's look at an example of a subgroup which is not normal. So let's look at S3. So the symmetric group in 3 letters. I define a subgroup. Consists of 2 elements. So one is the identity. And the other element interchanges, say, the first 2. Okay. So I claim this is a subgroup. Well, the point is that if I apply this twice, I get again this. So this element is its own inverse. And so therefore, you get here, so you have just a cyclic group of order 2. No, because 1, 2, 3, 2, 1, 3 squared is equal to E. But it's not a normal subgroup. Because I can just write it down. I just take some so if we take the non-trivial element here, 1, 2, 3, 1, 3, and say on this side I compose with 1, 2, 3, what do I want? 1, 3, 2. And I am supposed to take its inverse. But note again, this element, if I apply it twice, I get the identity. So that means it is its own inverse. Okay, so if I do this, what do I get? Well, how it does it go? 1 goes to 1, 1 goes to 2, and 2 goes to 3. 2 goes to 3, 3 goes to 3, and 3 goes to 2. And 3 goes to 2, 2 goes to 1, and 1 goes to 1. And you see this is not in this subgroup. So as I said, this is equal to 1, 2, 3. Okay, maybe it's now a good moment to stop. I don't know whether you have direct questions. Everything is clear. Okay, we can stop. I don't know how that works.